Now, in relation to strings, numbers are fairly trivial to talk about. Let's do it like this. Let's start out with integer based, then we'll move into the decimals, and we'll start with money, then decimal, then we'll talk about the approximates, right, the floating point. So let's come in here and let's say declare x to be a big int, and we'll set that equal to 6. You remember what big int was for? That was for the something like 900 quadrillion size numbers, right? It was greater than 2 billion. XY was your integer. So like, let's do this. Let's put out over here. So plus or minus 9 with a lot of zeros. I don't know. Is it quintillion maybe? I can't remember. It's something like that. Plus or minus a big number. Okay. The integer data type can take about plus or minus 2 billion. It's a little bit more, but you kind of get the idea if you keep that in your head. And then we take something like the small int. We'll make that one equal to 4. And so that one's going to be around plus or minus 32,000. Okay, you know, there's some small numbers, but they're not the main parts of it here. It's really 65,536, but you don't need to know that. But so if you look at them, we'll select X, Y, and Z. They give you exactly what you typed in. Like right down here, there's no reason, there's no advantage for going with a big int for storing the number 6, right? There might even be a disadvantage. How many bytes of storage is the big int data type? Well, we can actually, no guesswork, right? We don't have to even look at the documentation if we remember the data length. And I'm going to go ahead and copy that. And we say X and Y and Z. Okay. We can see that the big int data type took 8 bytes to present us this information. The integer data type took 4 bytes to give us this number. And the small int took 4. And what was the next one if I wanted to make another one? It would be the tiny int, right? So I guess I should have started with A or B and gone to B, but like A would be the tiny int equals 3, and that was 0 to 255, and then B was the bit, and that can either be a 0 or 1. So we say at A, at B, and now that I'm going to span a line, I'm probably going to do this. And sure enough, you can see now the difference. Now here's something interesting. Notice that the number of bytes, which is what data length returns, shows up as 1 byte for the tiny int, okay, which is 1 byte. But it also shows up as 1 byte for the bit data type. Why is that? Well, to represent a bit, it has to use an entire byte. One of the fallacies that I see people saying is, oh, you can save a lot of space by using the bit data type because it only stores 1 bit, which is not really true. You really could get a space savings if you had 8-bit data types versus 8 1-byte data types. To represent a full byte takes 8 bits. If you only have a single bit column, well, it really takes up 1 byte to represent that. It's kind of the smallest little bit right there. Okay, those are your basic integers. Not a whole lot to them. When we get into performance later on, we'll talk about the performance differences between using a big int data type versus int or small int. When we get into chapter 3 and start creating columns, we'll start talking about when I would use one over the other. Okay, that's the basics. What I want to really focus on for this video is what I think is the more challenging, and that is understanding all of the decimal types. So let's do this. I'm going to choose a different naming scheme. M is going to be money, and we're going to make it 1, 2, 3, 4, 5, 6, 7, 8. Okay? N is going to be small money. And we'll do the same. 2, 5, 6, 7, 8. Okay? And let's just kind of follow our same thing. So we'll say give us M, give us N, and I'm going to throw it all in the same thing here at M and data length at N. So we'll go ahead and put a go in here so it'll stop giving us errors, little syntactical errors. Oops, and I said select. I meant to say declare. Okay. All right. Now, if you will remember the differences here between money and small money here, let's just come over here and start writing it in here. This is 8 bytes, and it is plus or minus 9 quadrillion, I think it was. Just some big, huge number. Supposed to be 9 big number. And then the small money was 4 bytes, but it only went to plus or minus about 200,000. Now notice we still have 4 decimal places with both, and you can see the data length on each. Okay. Well, let's change this up. Let's now say 1, 2, 3, 4, 5, 6, 7, 8, 9. What's going to happen when we try to cram this big number into a small money data type? What happened when we crammed a larger string into a smaller variable that was a string type? It just truncated it, right? Well, when we do this, we're not going to get truncation. We're going to get an overflow error. It won't do that. Now, it's going to try, and it's going to do our query. It was successful in declaring this and then selecting this. Therefore, we get it actually returned. But it had the overflow error, yet it didn't stop the execution. It continued processing here. Okay, so we need to bring this down. We can chop this down to say 200,000, for example, and it'll work fine. And it still takes up the 4 bytes. And by the way, you should know this already from just knowing select statements. We can put the sign in front of these. These are not unsigned numbers. They do get returned as negative values as well. Here's what I want to ask you though. Let's say your business doesn't operate on 4 decimal places for currency. Let's say that you sell a product that is $1.95. Okay, somebody adds that in, and you've made, let's just even keep it a money data type here. So you've now said, okay, put this in here. You sell a product that is $1.95. So you declare sales price to be money equal $1.95. And when we return that, we get $1.95. You're being tricked here a little bit. Okay? If we switch this over to results to text, okay, notice right here, I guess it's not going to do it. There are actually 4 decimal places being stored. You have defined that this is a money data type. There are 4 decimal places. The people who wrote the SQL Server Management Studio made a decision when they did this in 2005. They said if there aren't more than 2 significant decimal places, we will actually only show the 2 significant decimals. Okay? For example, let's just show you this. We'll set it equal to $1. Let me rerun the query. Okay? There's not more than 2 significant decimal places, so it only shows 2 decimal places. Now, if we wanted to, we can actually see that it will go to 4 decimal places, but it's not shown by default. This is purely a formatting issue. Here's what I want you to know. There are an additional 2 decimal places here. You're storing $1.95, $1.96, $1.97. Okay? When you start doing some math and you start doing averages and aggregations over large numbers of these, are you going to start getting into that third decimal place or that fourth decimal place? If we added up 6,000 of these rows that were $1.95, $1.96, $1.97, and wanted to get an average price, will it only have two decimal places? Do you want to know what it is in the third decimal place or in the fourth decimal place? The point that I'm going with this is the money data type is fixed with 4 decimal places. You can't change it. You cannot make the money data type have only 2 decimal places. And for some people, me, for example, on the Learn It First website, that's a problem. We sell a product that only has 2 decimal places. I never want a third decimal point to be included in a unit price or a total when I'm aggregating several things. So what I do, I don't like the money data type as a representation of currency for my situation. I prefer decimal data type for 2-digit money, for 2-digit currency. And just so you know, I know we talk about this in the 160, that money data type is not typed to the US dollar or the Australian dollar. That has no effect on my query in this example. I could just remove the dollar sign and the query runs the exact same way. There it is with the dollar sign. There it is without it. Has no effect. Okay, so I prefer the decimal type for 2-digit currency. And what I would do is declare my sales price to be decimal. And so I could say something like 10.2 or 10, 2. I'd say select my sales price. And if you will remember the limitations here, what this is defining here is the precision. I'm specifying how many total digits will be in the output, including the decimal point. Over here, I'm telling it the scale, which is the number of decimal places. I can specifically tell it that I want it to go to 2. Now watch, if I pass in a value that is more than 2 decimal places, what's it going to do? It's going to round it up. So I'm guaranteed when I use a declaration like that to only have 2 decimal places. Now if I want it to be 4, I could do something like this. I could say 18, 4, which is roughly the same as the money data type. Now I'm specifying that I wanted it to go to 4 decimal places. And then you can start looking at your data length and you can see what the size of that value is. Sorry. If you want to see that it's 5 bytes right there. And we can actually make it larger. We can go up to, and you can't exceed it. Like I can't say I want to send back 18 total places, but 19 of those are the decimal point. You're going to get an error message. But so I could say I want 17 decimal places and send back 18, and then you send it back right there. And now it's taken up 9 bytes of storage. Now the float data type, you can start getting into that as well. So I could see declare. Some people can use a float, my float, and we'll just say it's a float equals 5, and select my float, and then data length of my float. You remember our float is the approximate, that's our floating point arithmetic here. And we can specify how many we want. So like I want to just say I want 4 as the total precision, which this is effectively a real. Float 24 and below is the exact same thing as the real data type. Okay. You're just defining the precision here. So specify it down here, run that again, okay. Brings it back. With float and real, these are approximates. They're floating point arithmetic rather than exact numerics like decimal or numeric. Again, we'll do more of this when we get into chapter 3 and start defining columns. We'll come back to some of these discussions.